In Boolean retrieval model, right, we were using this term document indices matrix, where documents are columns and terms are rows, and it is occupying too much space, and user needs a skill in writing the query. To solve the space issue, we have came up with the inverted index representation, where we are taking the terms and only the documents which are present, document IDs, list of document IDs where the term is present. And here the problem is the order is not guaranteed, or how many times a term is occurred is also not being represented. Memory issue is resolved, but these two problems are there. So the um, postings list is actually keeping track of the location. Location where exactly this term is being appeared, the term is appeared in the document also. With the locations, right, you can actually count how many times it occurred also. The positional index is solving that problem. To build a the inverted index, we collect data, then split the data into tokens, and then using a linguistic model we'll find the root words, right? Linguistic model means maybe a stemmer or lemmatizer, and then index the documents and create a database. Using this database we'll actually do the additional the queries. So if you take the inverted index as the representation, then the link the skip connections or the skip pointers will actually reduce the search time. So we understood these concepts to understand that data representation and searching sorting algorithms are also important to build an IR system along with the NLP, natural language processing concepts. So here we are actually looking at the NLP concepts, that TF-IDF, and the bag of words representation or inverted index representation, but we can represent data in a more sophisticated way. Using those sophisticated representations also you can build these systems, okay, where the query results will become more appropriate. Okay, so that we'll see later, right? It is like we are understanding the concepts, and application is a different thing, right? So we can see that. And then byword indexes are also there. They are uniword indexes, and you can have byword triword indexes also. When you have byword triword indexes, you will be able to do phrase queries very appropriately, right? Stanford University can be found very appropriately, rather than individual Stanford and individual university to try to find the two together. Okay, and in a longer query you may have to, if you have to find more appropriate results, right, you may have to have longer queries, sorry, longer indexes. The byword index will solve Stanford University problem, but if you want to find Stanford University Palo Alto, the index should be 4 words. So this is not possible, right? You cannot build byword, triword, and 4-word indexes for every problem, right? So that's where we looked into the rank retrieval model. Before we go into rank retrieval model, we try to understand the spelling corrections. Right? Spelling correction is also another concept in information retrieval. Basically, when a word is typed in the query string, the word may be right, may be wrong. We need to check first. That is the spelling correction. That is one application. The second application is a speech recognition model. After recognizing speech, it may be using that recognition or language translation model or speech to text model is generating some text. Right? The text may be right, may be wrong, contextually or individually. Right? Individual words spelling correction is called as isolated spelling correction. If you are trying to look at spelling with respect to other words which are surrounding it, right, that is context sensitive spelling correction. So in the Google, it is using context sensitive spelling correction. Okay, so soundex is one algorithm which is not used now, and the isolated spelling correction, edit distance, weighted edit distance, and Jaccard coefficient are the ones we use now. Edit distance tries to change the input word to the output word. Input word and output word are, output words are in the dictionary words. Input word is the word which is typed in the query string. Okay, so there may be 100 words in the dictionary which are close to whatever the word we typed, and we are going to take those 100 words and try to change this word to that word, right? First word, see what is the distance, now second word distance, third word distance, like that. Out of those 100 words, whichever is close, right, the edit distance is less, we'll take that as the spelling correction, and we suggest that as the spelling correction output, right? So that is edit distance. How this edit distance works? It uses dynamic programming. What is dynamic programming? This formula. So here in this formula, if you delete this word, this letter, and try to insert this letter, this much cost it's going to be. If you want to, if you don't want to delete anything and shift it and insert, then it's going to be this much cost. If you want to replace some character with another character, this is how much the cost is going to be. So at every step, from this is input, this is output, for every step, in the sense, for every character, we'll see how much cost, which operation is less costly, delete, insert, or replace. Whichever operation is less costly, we'll take that operation into consideration, and that way we calculate the total cost to convert this particular word intention to execution, how many steps it will take or how much cost it is. Okay, so yesterday we have seen that. So based on this value, right, we will decide which word is closest to this intention in the dictionary. So that is edit distance. In weighted edit distance, you will give different weightage to insert operation, delete operation, and replace operation. For different pairs of characters also, you can give different weights. That way, the distance measure is going to be more context. The maybe depending on the domain and the problem we are trying to solve, we may have to have different weights given to different characters also. Right, Jaccard coefficient we already know, right? We take a word or a sentence and convert into trigrams, and then see how much overlap is, right? If overlap is more, then they are similar words. If overlap is less, then they are not similar words. Intersection over union is the Jaccard coefficient. The same intersection over union is used in computer vision also. We'll talk about that. So there are methods implemented for all these in scikit-learn. We can use them. No need to implement them, right? And context sensitive search. So instead of if you look at this word, this sentence, flew from Hyderabad, flew will be there in the database, farm will be there in the database, Hyderabad will also be there in the database. But they are not. They are in this context, right? This farm is not the correct word, right? So from is the correct word. So how to find whether in this contextually this is correct or not? We need to take the closest words to all the words, all the tokens in the data, all the words in the data, right? All the words in the sentence, and then form combinations and see how many times the combinations have occurred, right? Whichever combination occurs more, that is the most contextually appropriate word here. So if you see the combinations, right, this combination occurred more number of times in query logs. So we said this is the most appropriate sentence, and this is the correct spelling of the form. Okay, this is a typo, right? FORM is a typo. From is a correct thing. So this is context sensitive spelling correction, and we are actually doing lots of combinations here and searching in the query log, so it's going to take a lot of time. So you can reduce the number of combinations here by looking by taking the most popular closest words and forming the sentences, and then take the most popular on the third one, forming the sentence, and see, right, instead of taking the least prominent words first, are all the combinations. We are taking most prominent words and forming the combinations and then trying to look into query logs. If it is occurring, right, most number of the times, then we take that as the correct spelling, right? This reduces the number of queries in the query log. Okay, so improvement on the a little bit of improvement on the context sensitive search. Okay, and then we looked into rank retrieval model. There are three ways of doing rank retrieval model. One is Jaccard coefficient, but Jaccard coefficient will not look into term frequency. There is an importance to term frequency, and there is a disadvantage also with term frequency. Importance is that if it is moderately occurring, then it is very important word. Less occurring, not important. If it is occurring too many times, maybe spam, right? Those three things are not considered by the Jaccard coefficient because it is based out of set theory. Whether the word occurred 100 times or one time, it is going to take the trigrams only once, right? So that way, this is not efficient in calculating the rank, right? It will give same rank to least prominent and most prominent and spam, all words, all different words. So that way Jaccard coefficient is not that efficient. So we are going into rank retrieval model where the most sophisticated rank retrieval models where bag of words is one way to represent data, right? In bag of words you will take count of words, how many times a word occurred, term frequency we call it as in a document, term frequency in a document. A word in a document, a word in a document, a word in a document. For every document, a word will have a term frequency. So term frequency, right? This is, take this particular document vector, take your query document and try to form this similar document vector for the query vector also, and then multiply the query vector with each of the document vectors. You will get numbers. And when you take query and form your vector and take the multiply that vector with each of the vectors, you will get scores. Whichever score is high, that is closest document to the query, right? So you can take bag of words or TF-IDF, doesn't matter, but bag of words is not going to be more appropriate. It may actually give more importance to the documents which have got a spam words or the stop words, right? If you have a stop word here, you may have highest count here, right? Most of the words are stop words in a document, you'll have highest score, and you take any query, multiply with this, you will get highest score. That way this document will come first, even though it is not appropriate. That's the problem we are trying to solve with TF-IDF calculation. In TF-IDF calculation, we'll take weighted term frequency. Weighted term frequency will apply log to the term frequency because a word occurring 10 times and a word occurring 100 or 1000 times are equal in importance, or maybe 1000 times 2000 times occurring word may not be that important, right? So it may be a spam word. So to nullify that additional unnecessary impact created by term frequency, we are applying log. That is called as word weighted term frequency. And we take weighted term frequency and inverse document frequency. Inverse document frequency is going to solve the problem of giving more importance to most frequent words, right? So a stop word may occur in all the documents, but it is not important. If a word is occurring in all documents, we will give 0 IDF score, right? N is the number of documents, DF is the document frequency, right? How many documents a word occurred. In a document, a word may be occurred 100 times, we don't care. We take one as count, right? 1000 documents are there. In all documents, is present. A word is present. We say 1000 is the DF, document frequency. Inverse document frequency is log of n by DF. So n by n is going to be 1 and log 1 is going to be 0. So For the stop words, we'll get 0 IDF. And we multiply TF and IDF, weighted term frequency and the inverse document frequency, and calculate TF IDF score. For stop words, you will get 0 score. For the words which are most important, you will get a better score. For the spam words also, you will get less importance. Okay, so that way we are mathematically solving the problem, right? In a huge corpus, you cannot manually look into it. So we are mathematically trying to solve that, and the TF-IDF is going to represent that. Okay. So if you are trying to classify bank forms, TF-IDF is not the right representation. Bag of words is the right representation, because in a form the names will be repeating all the times, right? So you should not give 0 importance to the words which are repeating, right? Or less importance to the words which are repeating. So bag of words may be better there. So you need to decide on the use case you are trying to solve. You need to decide TF-IDF or bag of words, right? So now I actually kind of used some terminology here. Consider each document as a vector of TF-IDF scores, right, of terms. Consider query also a vector of TF-IDF scores, like this, right? So I have taken the words for the in all the the TF-IDF score in all the cells we have got 0. Okay, and now we are trying to do a query, right? So I took the query document, and then the words which are present in the corpus, only those words we are considering in the query. If there are some words which are not present in the corpus, right, we will not consider. So that is another problem. If your database is too huge, then all queries words will be covered. If your database is less, right, the data is less, then this rank retrieval model may not work well. Okay, you should have huge volume of data, then only AML models will work. Okay, so you multiply. You actually take you multiply this vector with this whole matrix. You will get all the scores. You sort the data and take the documents and show it in the results. So that far we covered so far. Any questions? Any questions on information retrieval? Got it, right? You guys are clear of most of the concepts, right? I hope you said yes. Okay. So I'm moving on. So TF-IDF score can be calculated in different ways. Okay, computing vector scores. Unlike Boolean retrieval model, rank retrieval model will calculate score for each document and produce top k documents. Right, top k will be chosen in decreasing order of the scores. So you got that point. But TF-IDF score can be calculated in different ways. So there is a format of DDD QQQ, right? A document to document it is query. Okay. So what is this DDD and QQQ? So L and C, LTC, right? So that is DDD and QQQ. What is that, right? So term frequency, document frequency, and normalization. How do you do? Is there three Ds here? On the document, how do you calculate term frequency? First D. Second D is going to, second D, N means term frequency, normal term frequency you take. If I have N here, right, that means normal term frequency you take. If I have L here, I take log applied term frequency. If I have A here, I take this formula to calculate the term frequency. If I have B here, I'll take this formula to calculate term frequency. So different ways of calculating term frequency. Right? So do we have this mechanism in TF-IDF factorizer? Let us see. Okay, let me complete this and then I'll go. right? And then document frequency, how do you want to choose, right? So there are different ways of calculating document frequency. We have seen log n by df formula, right? It is inverse document frequency. Probabilistic inverse document frequency, right? There are different ways of calculating document frequency. There are different ways of calculating term frequency. There are different ways of normalizing the term frequency. Why do you need to normalize? We'll talk about that in a moment. Okay. So unit vectors we create of all the documents, and then we try to measure the distances. If you don't take unit vectors, even though the documents are same, you will get different, you will get a impression that they are not same and they are distant. So I'll talk about that in a moment. So how do you want to what is the kind of term frequency you want to take? What is the kind of document frequency you want to take? What is the kind of normalization you want to take? So here I took LNC and LTC. That means on the document I'll apply log as the term frequency. On the document, right? On the document means in the database document, I'll take document frequency is no. No means 1. I am not applying document frequency. Only term frequency is the log based term frequency is the one I am taking. And C, the cosine, right? C is the normalization I am doing. Okay, when you actually divide with your, this is what is this? Is this can I say this is L2 norm? This denominator one, can I say the L2 norm of a vector? Yes, no? Can I say this as L2 norm or no?
I think yes.
Right? So this is L2 norm. When you apply L2 norm onto a vector, what happens? V1, V2, two vectors, and you take V1 divided by square root of V1 square plus V2 square, comma, V2 divided by square root of V1 square, V2 square. The applied new vector is that unit vector. Okay, let me explain again. Okay, so I think you forgot. So let us take one example and try to understand this. Okay, so I have taken a document, right? Document is that a document means there is suppose that there is some text, right, in your database which has got auto term one time, car term one time, insurance occurred 10 times. Okay, that's the document which is present in your database. And the query string is best car insurance. I typed best car insurance in Google search. Okay, suppose that there are 1 million documents in your data. Okay, I think the best car insurance, a collection of 1 million documents where the document frequency of the terms is presented below. So if you take L and C as the mechanism to apply or find out the scores of documents, right, in the database, and LTC is the way to find out the the scores of the query, then this is how the calculation will happen. So for auto word, term frequency is 1. Okay, so I said L as the term frequency calculation. So 1 plus log of 1, that is 1. Okay, and best term frequency is 0. In the log term frequency, if it is 0, we'll take 0, right? 1, 10, like that. So I applied L as the term frequency for the document. If you have 1 million documents, for all 1 million documents, this is how I'll calculate term frequency. Okay, and then L, N, right? Natural, no document frequency, right? Document frequency we are not going to calculate. So I kept 1 for all, right? 1 means that whatever the term frequency we took, because ultimately the TF-IDF score is going to be TF into IDF, right? So 1 into 1, 1, 0 into 1, 1 into 1, 2 into 1. So I have got the total, the whatever document frequency, that ultimate thing as this whatever term frequency we got. Okay, when you say no, it's going to be term frequency only. Now we are applying the C as the cosine as the normalization. So what I did here, 1 by square root of 1 square plus 0 square plus 1 square plus 2 square. Let me write it down. So we understood unit vectors in our linear algebra. Now we are going to use it. So here, right, this value, right, this number I got when I did 1 divided by square root of 1 square plus 0 square plus 1 square plus 2 square. This I got because 0 divided by square root of 1 square plus 0 square plus 1 square plus 2 square. This number I got because, the same thing, right? 1 divided by. This number I got because I did 2 by square root of 1 square plus 0 square plus 1 square plus 2 square. So I'll say that this is a unit vector 0.41, 0, 0.41, 0.82. This is a unit vector. Will you agree? Will you agree? That's a unit vector, I'll say.
Yes, sir.
Yes, no?
Yes, sir.
I didn't get.
Yes, sir. Yes, sir. When we
So,
take the distance, then it will get 1.
yeah. So unit vector means what? That's the next question. So,
Yeah.
unit vector means, right, what? So let me try to take that example again, right? So right, v1, v2, x1, x2 is a data point. Then if you say that is a vector, there will be a length, right? So to calculate this length, this is x1, this is x2. Pythagoras theorem, that is square root of x1 plus x2. x1 square plus x2 square, right? So if you have to calculate length of this vector or L2 norm, it's going to be 0.41 square plus 0 square plus 0.41 square plus 0.82 square, right? This is 2 into 0.41 square plus 0.82 square, right? If you calculate that, let me try to calculate it and see whether it is a unit vector or not. So what is the use of unit vector? I'll talk in a moment, right? When I say something, there'll be meaning. There'll be some, additional thing to it, right? What is the use of unit vector? I'll talk in a moment, right? So for 0.41 into 0.41 into 2, right? This 0. Square root of, I think we can do that. I think we can do it here, right? So 2 into 0.41 square into 2 into, right, 2 square into 0.41 square, right? Right. So it is 2 to the power of 3 into 0.41 square into 0.41 square. For these two squares, we'll get 0.41. I think we can, I think I did not do it right. So plus, somewhere I missed plus there. Somewhere I missed plus there. Give me 1 second. Let me write in a neat way. You guys agree that, this is a unit vector. So I am just trying to see whether it is giving 1 or not, right? When you actually calculate the length of the vector, am I getting 1 or not? Let me write it clearly. I will not write clearly that. So let me take this. Square root of 0.41 square plus 0 square plus 0.41 square plus 0.82 square, right? So now if you multiply, if you add these two, what will happen? 2 into 0.41 square, huh? Right? Plus 0.82 square. Is that right?
Yes, yes.
So square root of, if I take 2 into 0.41 square plus 4 into 0.41 square. Can I do that? Can I do that?
Yes.
Huh? Now I take 2 into 0.41 square as common, right? 1 plus 2. I should get as 2, some kind of, I don't know. So 1 plus 2 is 3, right? 3. 6, right? 6 into 0.41 square. So this is going to be square root of 6 into 0.41. Square root of 6 into 0.41. Square root of 6. Yeah, see this? Almost 1.00 whatever, right? Got it? So that's a unit vector, right? We actually applied cosine normalization, right? Cosine normalization or L2 norm we applied. It became a unit vector, okay? Now on the query document, right? What is the mechanism? What is the, what are we applying? LTC. What is L? Log. In the TF score it is log, and on the document frequency it is IDF. T is IDF. So we calculated inverse document frequency with 1 million documents, log of the n by whatever document frequency, right? So I think I don't know how I took, but I calculated inverse document frequency here, and then TF-IDF score I calculated, and again C is the cosine is the normalization. So again unit vector I created. Now the query score, right? When I'm going to multiply this vector with this vector to find out how this document is close to this query, right? Query string. So for whole data in the database, we are going to use this mechanism to calculate the document vectors. And for every query we are getting in, we are going to use this approach to calculate the scores, and then we multiply and calculate the rank. Okay, that's how the rank retrieval model works. So let us see in TF-IDF, 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 TF-IDF vectorizer, whether we have all that, all those different mechanisms or not. Okay, let me take another slide. TF-IDF. Okay, so here C is norm L1, L2, right? What is that norm? After calculating TF-IDF score, which norm we want to apply? Okay. Use IDF score, right? Use IDF score is what? Now, do we want to apply your IDF score or not? Right here, if you say N, right, on the LNC, then you are not applying, right? If you say false there, it is going to be LNC. If you take L2 as the norm and use IDF as false, it is going to be LNC. Okay. Smooth DF, right? Sublinear TF. Yeah, this is actually weighted term frequency, right? This is false by default. Replace TF with, right, by default the default TF-IDF score is taking only term frequency. It is not applying, log there. So we need to say sublinear TF is equal to true, and smooth DF, right? Smooth DF is what? Smoothening technique. Do you remember? I actually spoke about smoothening in uh, uh, naive based algorithm. Naive algorithm, we did something to do prevent divide by zero, right? Do you remember? No. When the probability is becoming zero, we try to add, one to denominator and one to numerator also, right? That is smoothing effect. In some cases, if you are getting zero, right, zero count, to not to get a zero counts, right, we do, the IDF, right? So if a particular word is not appearing in any of the documents, then the DF is going to be zero. So not to get that zero, we are actually adding one. So that is the smoothing effect, right? If you look at this API, right, whatever we covered here, all will be present. Okay. The different ways of calculating TF-IDF score, some combinations you can actually do. These complex combinations you cannot do because the implementation is not present. Right? A, B, L, these implementations are not present in the scikit-learn. The reason they are not providing those implementations because maybe they are not that efficient. Maybe they are taking a lot of time but not giving much accuracy, right? That's why they are not implementing and providing it. Okay. So you got the whole gist of it, right? The total, TF-IDF and how to calculate different ways, and what are we doing on the query documents and the database and all that, right? Any questions? Okay, good. So the other scoring methods are also there, in vector space, right? I say vector space. We converted each document into a vector and a query into vector. So I am talking that in vector space terminology now. Euclidean distance is one way, right? Euclidean distance means, right, from now what we did, we actually multiplied directly one vector with other and took the score. Instead of that, right, you can actually take the Euclidean distance. What is Euclidean distance? Square root of this number minus this number square plus this number minus this number square plus this number minus this number square, this number minus, like that, it is Euclidean distance. But there is a problem with it, right? When if the vector is not unit vector, if the vectors are not unit vectors, if you haven't applied L2 norm, right, on the vectors, and if you copy pasted document one, right, suppose that, let me try to write it and explain. Right, Euclidean distance is one way to calculate whether documents are close or far. Okay, closest documents are the query results. Okay, but there is a problem. Suppose that there is a document, right, doc1, and you create a doc2 which is just a replica. This is just I copy pasted this content, whatever content is there, 4 lines, right? Those 4 lines I copied and pasted it here. Now if I calculate TF-IDF scores, right, TF IDF scores, right, I'll get double the IDF scores. There will be 10 terms of some car. Here you'll have 20, right? Like that, right? Ultimately, whatever the scores you will get double scores here on the vector. So when you try to look at the distance, right, it will show that there is distance, but are they really different? I just copy pasted the document one and created 2 pages of the same document, and then try to look at the query distance, document one and document two query distance, distance between document one and document two. I would have got some document. Is that really true? Is there a distance between document 1 and document 2? Did you get the scenario? Guys?
Yeah, so sir, when you copy, won't we get the distance as 0?
We should get distance 0 because the documents are same, right?
Yeah.
Euclidean distance, yeah, that's a good question. In the rank retrieval model, if you get highest rank, that's the most appropriate document, right? In the Euclidean distance measure, the 0 distance is the most appropriate, and highest score is the least appropriate. When you are taking Euclidean distance as the measure, you should be putting it in ascending order, not in the descending order. The rank.
Okay, sir.
Right? So here it is wrong. So when you actually calculate unit vector of this one and this one both, right? Then you get then you do Euclidean distance, right? You will get 0. When you convert this and this into unit vectors, right? They'll become same. The vectors will become same. Okay, that's the use of unit vectors. Got it? When you are actually applying norm, it is always suggested to apply L2 norm is good because it will create unit vectors even when the documents are same, right? The unit vectors will become same, and then when you look at the differences, right, it will give you 0, and then you'll be able to appropriately find the proper appropriate documents for the query search. Okay, so that's the importance of unit vectors. Okay, the next thing is cosine similarity. So here, right, in the previous example, when I said D1, a document with 4 words or maybe 3 words, and D2, a copy paste and created 3 pages of the same thing, 2 pages of the same thing. I said that there will be Euclidean distance between D1 and D2 when you are not converting the vectors into unit vectors, right? When you are not converting the D1 vector and D2 vector into unit vectors, there will be distance. Why that is happening is, if you look at in the 2-dimensional space, it will be like this. So the document 1 is going to be like that, and document 2 is going to be double the distance in the same direction. It will be double the distance like that. This is doc 1, this is doc 2. Okay, if you apply if you create unit vector, right, both will actually become, both will come down, right? The document 1 and document 2 both will be like that. Then you look at the distance difference, it will not actually, will have any problem. So this is one thing, right? The second thing is, if you are not interested, or if your data is you cannot apply unit vector, right? You cannot actually convert it to unit vector or divide it with L2 norm. Then what you should be doing is find out the angle between D1 and D2, right? D1 and D2, right? If there is some angle, right, that means the documents are different. If the angle is 0, then documents are same. Got it? So that is called as cosine similarity. The next measure, we call it as cosine similarity. Now cos angle, cos theta, sin theta, tan theta we studied, right, in our intermediate. Right? That cos theta will give you the similarity score, right? If the cos theta is 0, then they are completely same. It is 180, they are completely different, right? So 270, and in this in the other way around also, it is going to be same, right? Kind of similar, right? So let us see the cosine similarity. Cosine similarity is used very extensively. Okay, so here, right, document D, there are D1 and D2 query, the data points, right? Query is Q1 and Q2, right? The L2 norm of this document 1 and L2 norm of document 2 both we have taken, and then cos theta is going to be document 1 into document 2 divided by the document 1 into document, the L2 norms of document 1 and document 2. Basically, we are taking unit vectors and multiplying. That is actually giving you, instead of doing a Euclidean distance of unit vectors, we are actually taking unit vectors and multiplying them. That is giving you cos theta. Cos theta, zero angle, right? The value is 1. Okay, it's going to give you highest score, and at 90, zero value, and at 180 it will give you -1, right? The cosine similarity value is going to be between -1 and +1. If it is -1, they are completely different. If it is +1, they are completely same. If it is in between, right? They are kind of here and there. Got it? Got it? Any questions? Understood? Yes, no?
Yes, sir.
Okay, so cosine similarity is used extensively in whatever, right? So I have written some more notes here, right? You guys go through it. This is not that important. This is all about information retrieval and things. Somebody is interested or somebody need to build something, right? They can actually go through it. Okay, so that is about information retrieval, and in this concept, right, the cosine similarity, TF-IDF score, and the Jaccard coefficient, edit distance, weighted edit distance, these are all things used in NLP. NLP and information retrieval are same, one and the same, but in the scientific community they wrote it as separate things. They are interrelated. It should be in a single book, but so I actually followed Raghavan, right? This book to so this is the book I followed, right? And the rank retrieval model and all that is written very well, and there will be overlap. The machine learning algorithms will be mentioned in there, and they'll be talking about machine learning algorithms and all. Okay, so that's about the information retrieval. If you have any questions, I can answer. Okay, so I think you're good. Can I move on to the, yeah, maybe I'll take one example of topic modeling, right? Do you remember singular value decomposition? Should I kind of take a brief session on SVD? The next topic I'm going to talk about is topic modeling. If you get a document and you need to the algorithm need to output what topics the document is actually talking about. Okay, that is called as topic modeling. So we can use singular value decomposition to actually do the topics extraction. Okay. So should I go back to SVD and explain a little bit, or can I move on here? Maybe I have it here. So let us take a simple example here, and tomorrow also I'm going to explain the same thing. Right? Let me go through this briefly, and then we'll tomorrow also we'll talk about this more. So topic modeling, right? Information retrieval is over, and I'm talking about topic modeling. So what is topic modeling? A document is given. In that document, it may be talking about some topic a little more extensively than the other topics, right? So if you given a document, maybe it is talking about KCR or KTR or maybe Chandrababu Naidu or Jagan, right? So you can actually extract those names from it and show it. To extract exact names and show, we need to know named entity recognition along with topic modeling. But we are just looking at topic modeling now. And if you are interested, right, we can do a small POC on that. Okay. So singular value decomposition is a linear algebraic concept used in many areas, such as principal component analysis, latent semantic analysis, right? That's the technique we are going to use for topic modeling. Latent semantic analysis, okay? And latent representation means a reduced dimensionality representation or a converted representation is called as latent representation. There is some document or some vector or something is there, right? You are actually trying to mash it, munge it, and you came out with something that is called a latent representation. Latent semantic analysis. You are going to do semantic analysis on latent vectors of the original data. So you will create latent vectors by doing a singular value decomposition and recommender systems and word embeddings. In these 4 places, singular decomposition is used, singular value decomposition. That's where I said it is very important to understand. Okay, data mining and bioinformatics, the singular values, this latent semantic analysis is used. Okay, the technique decomposes given matrix into 3 matrices. Okay, so how it actually does it, we'll see in a moment. Right? Suppose that I have 3 documents here. Right? First document, I'm saying document, but it's a sentence. Okay, I have taken simple example here to understand the concept. And tomorrow, right, I'll show it on a bigger data set. So I have 3 documents. I enjoy machine learning. I like NLP. I like deep learning. Basically, it is talking about machine learning, NLP, and deep learning. So when you try to do topic modeling, it should actually output the machine learning, NLP, and deep learning. See whether it does it or not. Okay. So here I took count vectorizer. Right. What count vectorizer will do? It will take the individual words from the unique words from the data. Right. What are the unique words? Deep, enjoy, learning, like, machine, and NLP. I think I don't know why I didn't took I. I is also there, right? So I don't know why. Okay. So I have maybe it didn't took I. That's okay. We'll see that later. So fit transform I did and I got a matrix, right? So document 1, document 2, document 3 columns are deep, enjoy, learning, like, machine, NLP. Okay. So this is the vocabulary. So this is the order in which it actually took. Deep is the first word. Enjoy is the next word. Learning is the third word, like that. Okay. Now, if you remember the, principal component analysis, right? What did we do before we apply SVD P? SVD eigen decomposition. Before we did the eigen decomposition, what did we do with the data? Do you remember? Do you remember what did we do?
Stop word removal, sir.
Yeah, stop word removal. No, I am talking about principal PCA, sir. PCA.
Oh, okay.
While doing PCA, we took original data and did something before we applied singular value decomposition or eigenvalue decomposition. What did we do? We calculated covariance matrix, right? Do you remember?
Yes, sir.
Yes.
Yeah, let me open that, So these are all related, we learned all the fundamentals needed. Now we are actually trying to apply, okay? So this is very important. This is, from 3 months I'll take to explain and, create a strong foundation, and then I'll actually jump into the actual concepts. Okay, see here, I took the original matrix and then calculated centered matrix and then created a covariance matrix. This is covariance matrix. To create covariance matrix, I actually did centering. Okay. And then on this, we applied the eigenvector decomposition or singular value decomposition. When the matrix has got covariance, the eigen decomposition will extract covariance. Right? That's the point. Okay. You remember that point, right? When the matrix has got some meaning, when you apply eigenvalue decomposition or SVD decomposition, singular value decomposition, the decomposed vectors or the decomposed matrix will have essence of the matrix meaning. Here covariance. Okay. Because we are thinking that the strongly correlated columns have the strong predictive power. So we are trying to extract the strength of the correlation, which is nothing but covariance. Okay. But here, if you come to this topic modeling, right? What is topic modeling? If you have 100 documents, in all 100 documents, they are actually comparing maybe KCR with KTR, right? So if all 100 documents are comparing KCR with KTR, there will be some mention of KCR and then KTR, right? Right? Do you agree? In every document, there will be mention of KCR and KTR. Do you agree?
Yes.
And there will be some co-occurrence, or I shouldn't be saying co-occurrence. There will be one KTR, maybe 5-6 words, and then KTR. Maybe KTR again, 2-3 words, and again KCR, right? KCR son of KTR, and sorry, KTR son of KCR, and maybe this next chief minister maybe KTR. Like that, it's going to be, right? So there will be some some interrelation, or there will be some kind of words occurring together in a document will be there, right? So if you want to understand the topic of a document, the topic is going to be related between words. So you need to have a matrix that actually has word-to-word relationship. If you apply SVD on that word-to-word relationship matrix, then you get topics. Do you agree? Should I repeat? Should I repeat? Do you understand the concept?
Sir, so basically word-to-word matrix, you mean basically we need to build we need to extract that covariance
Yes,
or
yes.
the relevance, and then on top of that use the SVD.
Then we will apply that PCA, like PCA only, right? So here word-to-word relationship is what? Word-to-word relationship is the X transpose X is the word-to-word relationship, right? If you calculate X transpose X, if two words are occurring together, right, there will be some score. If the two words are not occurring together, then there will be 0 score, something like that, right? So X transpose is about document to document. So if you take X transpose X and apply eigenvalue decomposition, you will get the importance. Okay, but in either principal component analysis or in the latent semantic analysis, they'll use SVD because they take the original matrix, right? Original matrix is a rectangular matrix. If you have to decompose a rectangular matrix, you should be applying SVD, right? So the eigenvalue decomposition is not going to work, right? So if you apply SVD, right? If you remember SVD, let me go back. Where is that SVD? Not this one, right? Again, let me go back to SVD once. If you apply SVD, there is V matrix and U matrix, right? Which one talks about column relationship extract, and which one talks about the row relation extract, right? If think that think that your C is the rectangular matrix here, right? Your C is the rectangular matrix here, right? I applied SVD. Should I be taking V vectors or U vectors? Should I be taking V into consideration or U into consideration to, take the latent representation? X transpose X, right? X transpose X will give you document, the word to word relationship, right? So V will have the essence there. Okay, got it? Now, right, I am actually doing that. Here I actually tried to put that SVD again, right? So I did, linear algebra that SVD, right? SVD of X, and I have got Vs and Vh, right? V inverse it is, right? So this is V, which actually gives you the vectors, the extract of the word to word relationship. Now what I need to do is to find out the topic, right? The top topic. I need to actually take the features, and then I need to take this these rows, right? And the so the VH is the matrix here, and there is index, there is component. What is component? This is the component. That is the component. That's the component. Okay. So for first component is related to topic 1. How can I say? Sorry, the feature 1. I am actually zipping together the feature name and the component. Is that right? I am zipping the feature name and the component. Is that right? No? Yes? Basically, what are these? These are all, it's a 6 by 6 matrix, right? So these are all words, and these are all words, distinct words, right? So we can actually do that, the components and the features we can actually map. And then you know that, the topic 0 is actually talking about deep, enjoy, learning, like, machine, and NLP. Deep 2 is also talking about the same thing, right? So here the documents are low, so very, very less. So the score for each of these words is, kind of, distractive. But if you take huge volume of data, right, for each of these words you will get a, different score. So learning is the highest score one. That means the total, total documents, the set of 3 documents are actually talking about something learning. Okay, so like this, right? You can actually take the huge documents and calculate for each word some kind of score you calculate, and take the highest scored words and say that the documents are actually talking about that particular, that's called as topic modeling. Tomorrow we'll see our big data. Today, right, I try to show a simple example. I'll upload this and have a look at it, and you'll understand, what I was actually talking. There is nothing in there. We just applied SVD and took the scores and trying to take those scores and say that, the importance of the documents, importance of the total topic of the total documents. Got it?
Sir, from these scores, output what you are showing us, so what is that inference we can take? Is the conclusion is about the deep learning?
There are 6 topics in there, right? Okay. The first topic is about learning, and the next score is like, and next score is maybe deep. See that here? I sorted and took only 3, right? Learning, like, deep. Second topic is about like, NLP, deep. Right? Third topic is about NLP, enjoy, and machine, right? So machine and learning, it took a separate words. So before you apply topic modeling, you should actually, combine the phrases so that it will actually identify that phrase as phrase. Got it? So the best topic is, maybe out of the topics also we'll take the first 2 or first 3 only. If you have million documents, you apply topic modeling, you take, maybe 10 words from topic 1, topic 2, and topic 3, and then say the documents are, the total data is talking about those 3 topics. But here I showed everything. Your question answered, right, sir?
Yes, sir. Clear.
So this is a simple example, right? When you take a bigger data set and try to work with it, it will be better. But when you apply SVD, right, on a big data set, it may actually memory issues may come. We need to use. I think there is this topic modeling LSA will use partial SVD. I forgot the name. I forgot the name of that SVD. Truncated SVD. Truncated SVD will take batch-wise data and try to do it. But on a big data, right, it will anyway create problems. Try to experiment with it and see. Right. On this big data, the numbers are very confusing. So I created the small one so that we'll get more clarity. So there are scores, and we have actually taken 10 only, and this is on a healthcare data set. It is actually talking about Pfizer, patients, some medicine, cancer, right? So I think we have taken maybe 100 documents there, because when we took huge data, it was not working. So we took only 100 documents and tried to work on it. So those 100 documents are actually talking about Pfizer company. And the second topic is about something. I don't know what these are. Maybe they are related to healthcare, I think, those words. Okay. So tomorrow we'll see this, and once this is done, right, we can actually jump into deep learning. Mostly tomorrow we'll start deep learning. Mostly, right, by 8:15 we'll start deep learning. Okay.